and talk about little about the data processing, model architecture, training process, and testing and results. So in the data processing, as I mentioned that it consists of 15 data points. Each sequence represents the input of the model at time step, whereas the target output is the next values of the time series. Now let's talk about the model architecture. It has mainly two main layers. It has two main layers: two simple RNN hidden layer, with one being a dense fully connected out, and another so it has basically two simple RNN hidden layer, and the another one is the output layer. Simple RNN layer with 50 units aims at capturing temporal dependencies within input data. On the other hand, the output layer predicts what is happening next with the given sequence. The model use can be summarized down. So in the Python code, which is the model construction. So here mainly it uses model, which is the sequential model, and it has the simple RNN. 50 is the number of the neurons in the hidden layer, and it defines the input shape and dense. And the other one, and the second simple RNN you can see is the second layer. So let's come to the training. So in the training, the model was trained over 20 epochs with a validation split of 20%. The training process focused on minimizing the mean square error between the predicted and the actual sine values using ADAM optimizer due to its effectiveness in handling gradients on noisy problems. And the next step was testing. So here the model was tested against the testing data to check the performance. So let's come to the results and discussions, which is the test results. So in this, the model prediction was plotted against the actual sine wave to visually access the information. The resulting graph is as shown here, is a very close alignment between the predicted and the true values, indicating that the model has learned the underlying pattern of the sine wave very efficiently. So coming to the graph, here the blue line, which is below the orange line, is the true values, and the orange line is the prediction. So you can see that it has predicted very efficiently. Let's go to the next slide. So let's talk about a little on vanishing and exploding gradient problem. So the vanishing gradient problem occurs during the training of deep neural networks. Excuse me. So the vanishing gradient problem occurs during the training of deep neural network, where gradients computed via back propagation diminish to very small values as they are propagated back through the network layers. This happens when the derivatives of all the active function used in the network are less than 1. Each layer gradient is a product of subsequent layers gradient due to the chain rule in calculus. When these small derivatives multiply through many layers, the resulting gradient can be extremely small, effectively vanishing. This makes it very different for the neural networks to learn and update the weights for the early layers, which can severely slow down the training process or lead to the poor performance, especially in networks that need capturing long range dependencies. So that is mainly the vanishing problem. So now let's talk about the gradient explosion problem. So on the other hand, during the back propagation, there can be an exponential increase in gradients across different levels of a network, known as exploding gradient problem. This usually takes place when the derivatives are greater than 1, leading these gradients become very large. Consequently, this causes massive updates in the network weights, thus often resulting in an unstable net. At worst, such a situation may cause the learning process to diverge completely because of the weight values will have grown too big for the management. So as you can see the graphs here, so on the right side you can see the exploding gradient, so where you can see the values have become very large, so it is very hard to manage those, and it doesn't capture the input data input, and it doesn't capture the input and the output data properly. So on the left side you can see the vanishing gradient. Here you can see the values have become very low. So because of this, the neural network cannot memorize the starting of the sequences, and this becomes a problem. And this becomes a problem. So now let's talk about the LSTM solution for RNN limitations. So before going into this topic, let's talk about what is RNN's limitations. So the first thing for the RNN limitation is a lack of short memory. Simple RNNs cannot handle long input sequence well due to their short memory problem caused by vanishing gradient issues. It means that the information from the earlier time steps cannot be carried over to later ones easily, since the network fails to capture those long range dependencies within the input data. Problem with the gradients is these networks suffer most from both vanishing and exploding gradients as mentioned before, which makes them difficult to train on deep or lengthy sequences, thus restricting their usefulness when applied to complex sequence modeling tasks. So the next one is the capacity constant. Compared with LSTM among the RNN variants, simple RNN possesses a simple structure, hence its limited modeling capacity. This implies that they are not good at discovering the complex patterns in a data as much as more advanced types do. So as we now know the limitations of the RNN, now we'll talk about how the LSTM designed to solve the vanishing gradient problem and capture long range dependencies better than simple RNN can. They address these problems along with the simple recurrent neural network limitations in several ways. So the first one is the memory cells. So LSTM introduced a memory cell which could retain information for an extended periods of time. So these cells are regulated by gates. So now let's talk about the gates. There are three kinds of gates used in the LSTM, which is the input, output, and the forget gates that manages to inputting or outputting the data into or from the memory cell. This allows the network to decide when should the content be updated, exposed to the rest part of the net, or even forgotten if no longer needed, which is from the forget date. So let's talk about how it deal with the vanishing gradient. By preventing too much cutting of the gradients during the learning iteration via forget gate, the gate mechanism helps to keep a stable gradient across many steps where it would have vanished otherwise, which is essential for the learning long-term dependencies, copying with long-term dependencies. So the next one is we'll talk about the coping with exploding gradient. In this situation where we have the exploding gradient, there exist methods such as gradient clipping in LSTMs, whereby any gradient exceeding some threshold is reduced before applying updates, so as not to destabilize the learning process. So incorporating incorporating these steps ensure that the LSTM deals with the gradient issues better than gradient issues encountered by the simple RNNs, and increase the ability of the network to represent across lengthy input sequences. Let's talk about the images. So in the right side you can see the long short term memory. This is how it has. So you can see it has C gate, which is the cell state, and it has input, output, and forget gate. It has input, hidden states. So this is a structure of long short term memory. And on the left side you can see a vanishing gradient problems where where it becomes very hard for the model to remember the starting part of the sequences. Let's go to the next topic, which is prediction of the Apple stock price using the LSTM network. So here it